It's always fun giving a talk at one of the Hyperledger meetups, just if for no other reason the fact that I look out and it's like, I probably know half of you or have discussions with half of you about the different things that we're doing. So it's kind of like, coming home and giving a talk to a bunch of people that you know that way. Today, we are going to talk to you a little bit about Fabric Private Chaincode, and there's sort of a cast of thousands, well, at least 5, that are working on the project. So Jeb and I are going to be doing the presentation today. Marcus and Bruno, hands up, guys. Okay, they are going to be showing you how awesome and incredibly cool this is in a live demo at 5:15 right next door. So everybody make sure that you pack up and just walk like 50 feet over there to the next room for that. Shweta and Jordan and Michael Steiner are the other developers who are all part of the project as well. So what I want to talk to you about today is this collaboration that we've been doing around bringing together some of the best of Hyperledger Fabric and some of the benefits of trusted execution environments. And what we get from Fabric is sort of the industry-leading blockchain strengths for resiliency, for development and engineering, deployment, management tools. And what we get from the trusted execution environment is some performance optimization or efficiency optimizations on the integrity part of it. But really the benefit that we get, and the thing we want to talk to you most about today, is we get another level of preservation of confidentiality. And it's our belief, based on the things that we've seen, that this opens up an opportunity to build a whole new class of applications for blockchains. So just sort of retrospective about what Fabric provides for you already in terms of kind of privacy and confidentiality. And by the way, I will generally use the word confidentiality when we're talking about this, largely because privacy has all of these sort of social implications that go along with it, and contextual integrity and all of the other things that we talk about. So I want to kind of leave that part aside. So what we're really talking about is how do we protect information? How do we protect and limit access to the information? So when we look at Fabric today, we've got, people usually talk about a couple of different kinds of things for doing confidentiality in Fabric. One is the basic characteristics of limiting access to the information. This is, the word we've been using in the architecture working group is segmentation. So we limit the total number of people who have access, who have physical access to the data. And obviously, we can always use encryption. And what encryption really is limiting physical access to the keys that unlock the data. So it gives us a little bit more efficiency for access to it. So what we get for segmentation from Fabric right now, there's sort of a coarse-grained approach, which is channels, which gives us sort of a high-level scope on the set of participants who can access the chain code. At a much finer grain on kind of a per transaction basis, we can also use private data collections, right, which we can associate with the transaction. When we use channels and private data collections, what we're really doing is saying that there is a limited subset of the participants in this network who have access to the data. And at a minimum, in the case of the channel, it's anyone who participates in the channel. So all of the peers who are participating in that have access to it. All of the participants, conceivably, who are interacting with it, have access to the information. When we use the private data collections, at least those who are participating in the transaction, plus the endorsing peers, have access to it that way. When we do encryption, we like to talk about encryption as being, sort of this next level of access. But really what encryption really is just limiting access to the keys. Because once you have the key, you have access to the data. So what we get by doing encryption is, instead of moving around big chunks of stuff in order to share, we move around a little key, and we can move the big chunks of stuff separately. But as far as visibility to the data, still amounts to the same thing, right? At the end of the day, when we write these applications, whether we're using channels or private data collections, what we're really doing is just limiting it to a well-known set of participants. And in particular, the endorsing peers have to have access to the data if the transaction has dependencies on that data. So if the semantics of the operation require access to the data, then the endorsing peers have to be able to see it. And what that means is whatever the owner of the server is where that endorsing peer is running has access to that data. So, what happens when no one is trusted with the data? Right, that's really the core of what we want to talk about here today, is what happens when no one's trusted with the data. I still need the integrity of the endorsement, but I want to protect the access to the data so that even the host of the endorsing peer doesn't have access to it. And so what I want to do is to start with just some usages that kind of give you a flavor for the kind of applications that we're talking about when we talk about this class of no one is trusted with the data. So a couple of years ago, we were asked to do a prototype using some of the private data objects code of a real-time insurance quotes for drivers. And the basic scenario was automobile ownership is going through sort of a transition, especially in Europe, where we're going from sort of long-term own your car for 10 years, build up a profile for it, you have a single relationship with an insurance company, to something that becomes much more transient. You know, we've got things like ride sharing and automobile rentals that tend to be short-term. So if I'm just doing ride sharing and rentals, then how does the insurance company develop some feel for what my real risk is? Because the information about me as a driver doesn't exist in any single location. So, you know, one of the ways that people are, that insurance companies are trying to make this work is, you know, they give you the little dongle that plugs into your, what's it, the QDB, whatever it is, the little port that's under your dashboard, right? And anytime you drive someplace, it watches what you're doing, and, you know, when you brake hard, it sends a little alert to you, and when you accelerate too fast, it says something that you're doing, and you're speeding in someplace, and it sends the alert, and your insurance company gets absolutely everything about you. And we're really comfortable with this, aren't we? Not me. But imagine the situation where I don't have that long-term relationship with the insurance company, that each one of these interactions that I have with a car is based on the driver profile that I have. Well, I can tell you that the way it works right now is you go into Hertz and you say that I want the insurance on my car from Hertz, and they will give you the absolute maximum risk rate, right? So you're going to pay through the nose. Doesn't matter how good a driver you are, that's what you're going to do. So we would like to be able in a situation where we can collect all this information about me as a driver across all these different vehicles that I'm doing. And I want to package this thing up and hand it to an insurance company. Well, okay, we'll get to hand it to the insurance company in a minute. But I want to take this profile, hand it to the insurance company. The insurance company looks at it and says, hey, look, you know, 6 months, even though you've driven 9 different cars, no accidents, you never speed. You stopped appropriately at every stop sign. You did all the things you're supposed to do. We love you. Here's a great quote. That's what we would like to be able to do. There are a bunch of problems with that. One is, how do I ensure the integrity of the profile that I build? That's out of scope for today. But really the question becomes, how do I get this profile to the insurance company? Because I don't have a relationship with the insurance company right now. I'm looking for a quote. I'm looking for a quote that's going to last for insurance rate for 3 days while I rent my car. So how do I do this? Who do I trust to run the computation that would match my profile, which is all of my personal data in every place I've been, with some rate analytics that the insurance company has provided in order to generate quotes? Well, it's my profile, so the insurance company should run their analytics on my machine, where I can make sure that my profile is safe. Right. The insurance company is going to trust you to run their computation on your machine and give the right answers back. No. What about the other way around? I'm just going to ship my profile off to the insurance company. I'm going to trust the insurance company to do nice things with my profile. Okay, that's kind of how it works today, but none of us are really very comfortable with shipping our profiles and our detailed information off to insurance companies, right? Yes, they're supposed to get rid of it, but do we really believe that they actually are getting rid of it? So what we really want is some trusted party. And again, I'm going to talk for a moment about the idealized trusted party. What I want is a trusted party where I can ship my data and the insurance company can ship their analytics. The computation happens and nobody gets to see the data, but that the rate quote that comes out is one that both of us trust. It's the integrity of the computation without exposing the data that was used to make that computation. So, second example, and this is the one that Marcus and Bruno are going to show you in a little bit, is this kind of sealed bid auction. You can imagine the idea of a sealed bid auction is it's totally blind. Nobody gets to see what others are bidding. We don't get to see the high value of the auction. And of course, there's no collusion, and the auctioneer is a completely independent third party and completely trusted in this case. And of course, you know, the examples of this are things like spectrum auctions, where the value of the spectrum being auctioned is measured in, 8, maybe 9 digits. This is highly valuable assets. So the potential threat is very high for it. The temptation for fraud is extremely high for it. So what we do right now is we basically take some government agency and we put them in a position of authority, and they run the auction for us. What happens, however, let me just point out one thing, because this is kind of the critical point, which is that from the time I start accepting bids until the time the auction is closed, in theory, no one is allowed to see the current state of the auction. Because anybody who can see the current state of the auction has a potential for fraud. Now they can start to manipulate the auction. So what we end up doing is right now is we have to institutionally trust the auctioneer for doing that. And okay, we've got legal recourse and a bunch of other techniques that we can use to sort of make sure things are done correctly. But even if I trust the organization, do I trust all the individuals in the organization? It is often the case that what we want, even as the auctioneer, is plausible deniability. I don't want the responsibility of being able to see the state of the auction, because if I can't see the state of the auction, then I can't be held accountable for any potential fraud that happens down the line. So if I want to move the auctioneer out of that center of trust, then I have to go back and I have to create this trusted party again. And what are the characteristics of the trusted party? This should sound familiar. We want to make sure that the trusted party enforces all of the rules of the auction. And by the way, sometimes these spectrum auctions are really complicated things. And Marcus and Bruno are going to give you a little bit more insight into the kind of details of the example that we implemented in FPC for it. So these are complicated things. We want to make sure that the integrity is kept. But we also want, especially during that time from the beginning of the auction until the time the auction is closed, we want to enforce complete confidentiality on the data. And in particular, there is no one who has the right to see that data. This auction may last over months, so it's not like we can just stick it in a server and expect the server to be continuously running. There is no one who's allowed to see that data, and we have to have long-term persistence of it. Okay, so third example is organizational elections. I'm staying out of the political election space because that's like loaded with a whole bunch of other problems with it. But let's just talk about electing something like, say, the Hyperledger TSC, right? So how do we work this today? Right? There's a set of rules for who gets to participate. There's a set of rules for how you get to vote and how you sort of allocate your weights on your votes. By the way, you all should vote in the TSC election in the fall. Does that work for you? Okay, thank you. So this is lovely. We would like to be able to do this. And typically the way that we do this is, and this is the way the TSC has been elected, is that there's sort of an elections committee, which at least involves RAI and the Linux Foundation, the Hyperledger staff, in order to manage that election. But the critical thing about the election is, from the time we start accepting votes until the time the election is closed, which was, what, a week last year? Something like that. For that week-long period, no one gets to know the state of the election. No one gets to know, or no one has the right to see the data that we exist in there. Okay, so this really means the way that we do this is we trust the election staff, unless you're the TSA, in which case they have to add the observers as well into the trusted computing base. But okay, now that we've removed both the sort of observer class and the TS and the election staff from the trusted computing part of it, or the trusted part of it. Now we can speculate on what this trusted third party looks like again, right? And so this should sound familiar. We need integrity. We need to make sure that every vote is counted. We need confidentiality. And in particular, we need confidentiality from the beginning of the election to the end of the election, and no one gets to see this. So let's think a little bit, just step back for a minute and think about what Fabric would give us. Fabric gives us the segmentation pieces of it. We get channels and we get private data collections. How would we do the implementation of this trusted third party with Fabric? And the answer is, unless we trust the peer and the host of the peers that are doing the endorsement, we can't. Because the peers who are executing the code right now, even though they have been segmented into channels or the private data collections or whatever we want, they don't have the ability to do this because they can always see in it and they can always be held accountable for the information that they potentially saw as part of that computation. So again, sort of summarizing, what do we need from the trusted third party? We need to ensure that the right chain code executes. We need to ensure that the results were computed by the chain code that we thought was executing. Clearly, we need to protect the participants' data from other participants. All of those three we get from Fabric already. But what we don't get is that last one, which is, at times, we need to protect the chain code data from everyone. So what we're proposing is this thing called Fabric Private Chaincode, which, Fabric plus trusted execution environment does really cool things. Basically, what we're going to do is take the chain code that you know and love and execute it inside a hardware-based trusted execution environment. So what we get for integrity is what we've been saying about Fabric gives us the endorsement policies we need for resilience to attack. We get the assurances that come along with that. TEE attestation actually allows us to do some acceleration and some improvements in efficiency. Again, that's sort of out of scope for this talk right now. But there is some benefit that we get even on the integrity side of it. For confidentiality, again, the participant-to-participant thing, we already have Fabric and channels and private data collections. That works. But the TEE gives us that last requirement, which is it protects it from everybody else. We're going to trust the encrypted memory that exists in the TEE. So for those of you who are not familiar with what a hardware-based trusted execution environment is, the simple way to think of it is that it's a chunk of memory that is encrypted, and that memory is encrypted with a key that only the hardware has access to. So the owner of the server, the owner of the computer does not have access to the key that's being used to encrypt that memory. There are a couple of other features that we like to find in it as well, mostly related to hardware attestation. So the encrypted memory gives us a way of preventing even the owner of the machine and any other software that's running on that machine from seeing into some segment of memory that we're going to be executing out of, which means we can put keys and secrets and data and other things inside this encrypted memory, and you can't see in order to manipulate it or to read it. The hardware-based attestation basically says, here's what we loaded initially, and we can verify that what we loaded initially is correct and that it hasn't been tampered with from the outside. Okay, so it's those two properties that are important. Here's what we loaded. We know and can verify that what we loaded was what we agreed to load, and we've prevented any modifications to that while the code's being executed inside that environment. So what we really get out of this is we get a protected place to execute code where the host, the owner of the machine, is not able to see into the execution, but where we can guarantee the integrity of the computation that takes place. Okay, so just some common features that we have. We get the confidentiality, as we talked about. We get the integrity from the measurement that happens, and we get third-party attestation. And the third-party attestation is really sort of the critical part for trusted execution and blockchain environments. I can prove to you that I made the right computation. So this is where I get the integrity from. So I'm going to turn it over to Jeb here. Basically, what I want to say is, to conclude my part of this, is our goal in developing FPC was to make it as seamless and transparent as possible for Fabric developers to take the chain code that they've been building and run it inside FPC with the minimal change as possible. I will point out that doesn't guarantee confidentiality, and we'll talk about that in a little bit. But but at least from the purposes of protecting the secrets while they're executing in the chain code. That's our objective. Jeb?
Is this on? Okay, thank you. All right, so this is a brief sort of top-level overview of elements that are added in Fabric Private Chaincode that are not in Fabric. But rather than just go through the detail here, I'm going to go through it bit by bit over the next few slides. So with that, what you see here is it emphasizes in green elements that have been added over and above what you already have in Hyperledger Fabric. So just going through these a bit at a time. Over here in the client, you see we've got an SDK extension for interaction with Fabric Private Chaincode, FPC. You see the chain code here now executes in a chain code trusted execution environment. There is another trusted execution environment in which we keep a trusted ledger, and we'll talk more about what that is and what it does. There's some additional validation logic that's added to the transaction validation. Again, we'll go into more detail. And then finally, we have a piece that I'll describe a little bit more here called the Fabric Private Chaincode Registry. Now, this view assumes that we are already set up. FPC is already in place. And what I'm going to do is use this to walk you through not every technical element of FPC and how it works, but just sort of the life cycle of a single transaction, because that shows you basically how the system works. And for those that want much more detail on how you set up the environment in the first place, I'll refer you to our RFC, or we can talk afterwards. The one thing that I'll point out here is the FPC registry that I mentioned down here. This is a standard Go chain code, but it records a view of essentially a list of the chain code trusted execution environments that have been registered in the system. So without further ado, we'll go into a little bit more step-by-step in the life cycle of a chain code transaction. So invocation and response is basically Fabric standard, with the distinction that now the payload of the invocation and the endorsements is encrypted. It's encrypted and authenticated. Now, when you do the invocation, the client contacts the chain code through this little element here called the chain code library, which is itself a shim. It's a C++ shim, since as, I don't recall whether you alluded to this or not, in the initial version of FPC, the chain codes have to be in C++. That'll change over time. So we invoke that, we invoke this through the chain code library shim. And the one additional element here is that the chain code, when it does a get state, it not only grabs the state from the ledger, but it also goes through a step of validating, verifying the state through a query to the ledger trusted execution environment. And it will come back around in a minute or two to tell you how that is formed. But essentially, what it stores is an additional ledger with information about security, essentially security metadata for the world state. Now, like I said, we'll come back to that in a minute. So once the client collects the necessary endorsements from the peers, it forwards them up to the orderer, and this is basically just Fabric standard. The difference, of course, is that the data is encrypted, and it includes in it the information from the attestation of the chain code that it's using. Now, I didn't really go into this in much detail, but remember when we started, I mentioned that the FPC registry contains information on the attestation of each chain code that has been registered in the system. So when this endorsement comes back, it includes that attestation information. So the orderer then forwards the ordered transactions out to the peers for validation. And in particular, there's no actual changes to the orderer, the way it operates. It does include the attestations and in the endorsements. The transaction validation first proceeds as normal, standard for Fabric, but then in addition to the standard validation, it executes another set of validation. We add this FPC validator to the standard validation, which essentially verifies that the transactions are actually signed by a valid chain code TEE, which is registered in the FPC registry. Okay? Now, as I mentioned at the beginning, this FPC registry maintains this list of all the chain code TEEs on the channel and their attestation information. Now, having done that, once the transaction is validated, it forwards that transaction to the ledger TEE, which essentially performs the validation over again. Now, there's a little bit of lack of efficiency, and we're talking with several people, getting advice on how to make this more efficient in future versions. But essentially, in order for us to have a fully trusted view of the world state, we need the transactions to be validated again inside the trusted execution environment. And once that is done, it then essentially records security metadata, basically a hash of every key value pair in this trusted ledger. That, as I mentioned at the beginning, when we did the invocation and endorsement, that's what enables every piece of world state to be validated based on the trusted ledger. So you get state from the regular ledger, then you check that the security metadata in the trusted ledger matches up. If the hash value recorded in the trusted ledger matches the hash value of the information in the regular ledger, you know it hasn't been tampered with. And then finally, the fully validated transaction is committed to the ledger. Okay. And with that, I will pass it back to Mick for the last couple of slides.
Oh, I'll let you. Yeah, you can keep it. I got this one. Where are we at? Okay, so we're in good shape still on time. So, yeah, I'm still alive. So one of the things that I said earlier, and I just want to come back and re-emphasize it here, is that one of the goals of FPC is to make it possible for you to develop the chain code that you've been developing with all of the tools that you've been developing, just like you've been developing it before, and in this case, be able to deploy it to peers that are enabled with FPC. And as a result of that, you're going to get a bunch of benefits related to the fact that the values that are stored in that ledger are going to be encrypted, and only the chain code that's executing inside FPC is going to be able to decrypt that. So what we get, and our goal for you, and what we're trying to give you, is a consistent deployment model with what you've seen for Fabric. That is the same set of client commands should work that they've been doing. A consistent development environment, which includes the shim library. And let me just say that not everything works quite exactly the way it's supposed to work. So for example, range queries are rather difficult to do over encrypted data. And so we're not doing range queries for that. But you should be able to operate on sort of key value store in the way that you would expect to execute on it. Right now, the support is exclusively for C++ on it. That's mostly because it gives us a way of easily compiling that code to execute inside the enclave. Eventually, the goal is to be able to support the same set of languages that you would have available to you for other Fabric applications that way. So one of the things that I said earlier is that just because you take your chain code and deploy it in FPC does not guarantee confidentiality. It's not like we get to sprinkle a little magic dust over it and suddenly everything works the way that we're supposed to work. Some of the problems are obvious, right? So if I have a counter, let's say that I have an operation which says, give me the high bid on the auction. And that high bid is confidential during a particular period of time, but I allow you to execute that transaction or retrieve the information, externalize the information about the high bid. Well, we've validated confidentiality, but you kind of did it because you were supposed to do it, right? Because that was the way that you wrote your chain code. So some of these things are pretty obvious, right? Don't externalize data that you expect to be maintained confidential. Some of them are a lot more subtle. Right, that there are some times that we end up with sort of synchronization operations. So I know, and I'll speak a little bit more from the private private data objects, which is one of the sources of some of the ideas for this. When we do things like a k-anonymous means or a differential privacy implementation inside the chain code, and we want that policy to be continuously enforced, there's a query budget that goes along with it. So the style that we've implemented in PDO in order to make that work is a commit reveal style. So you commit to the query that you want, the query budget is decremented, that state gets saved, and in a separate operation that verifies the state's been saved with the query budget being decremented, now we allow you to see the results. And so there are a few things like this that we have to be a little bit careful of how we design the applications. So it's not, like I said, it's not just sort of, I just pick it up and run it and suddenly I get confidentiality. There are times and for different kinds of operations where I have to be a little bit careful about how I architect it. One of the things that we're providing for you that's in progress right now is a developer's guide for some patterns for how to build confidential applications that go along with that. All right, so I'll let you finish it up.
Just a few last words.
Oh, by the way, did I mention that Marcus and Bruno, who are in the back, are going to be doing a big demo on the sealed bid auction at 5:15 in the room next door?
Absolutely. Wave your hands one more time, guys. There you go. All right, we'll all troop over as a gang, hopefully. So with Fabric Private Chaincode, you can write chain code that is protected from view, even from the peers, from any participant in the ecosystem, essentially. It becomes a trusted party, which in cases where you don't need anybody to see the data, in fact, you need the data to be protected from visibility from everybody participating in the operation. And this enables new classes of DLT-based applications like the ones you saw here. And it's interesting, just in conversations we've had here today, we've probably found 2, 3, maybe half a dozen new and interesting use cases. I mean, in the grand scheme of things, we believe that trusted execution environments are going to be used more and more. There's an analogy we sometimes use to HTTPS. You may have heard some of you have heard us say this already. Years ago, HTTPS was invented basically to enable secure web transactions with credit cards. But once it became easily accessible, people realized, why not just use it for all web traffic? It's just easier and everything gets more secure. We think over time, something along those lines may happen with trusted execution environments as they mature. We hope to be contributors to that. Speaking of contributors, we hope that you will join us. Check us out. Our repo is on GitHub here, Fabric Private Chaincode. There are links on the repo to the other resources like the wiki and the paper. And we hope that some of you will bring your interesting use cases to us and join us and participate on the project. Please get in touch with us. Please troop over next door with us and watch the cool demo. And with that, we'll open it up for questions.
Between Avalon and FPC. So I picked my usages very carefully. The first usage that we were talking about with sort of the insurance quote, because you're doing essentially a one-time computation where there's really no state that's managed other than the profile. And again, we'll keep the profile out of this, but the actual computation of the rates. I've got some confidential data I want to perform an analysis on. I want that analysis to happen in a confidential environment. That's a great application for Avalon as it works right now. Avalon, transaction to transaction, and Avalon is stateless in its current implementation. FPC is designed for stateful interactions, right? So as I accumulate, so with the auction, I accumulate bids over time. I do some computation, and I accumulate some more bids. And I do some additional computation, I accumulate some more bids. So the state is maintained over multiple transactions. That's what FPC is good for. And so for the moment, when we're talking about sort of stateful, you can use the words on-chain and off-chain. I really don't like those at all, because in theory, all endorsement in Fabric is off-chain, right? The order is the only thing where there's a notion of a chain. So you can think of it that way, but really the way I prefer to think of it is Avalon, in its current form, is stateless. I can perform those computations. FPC is stateful in the sense that I'm actually changing the state of the ledger as I perform the transactions. Okay?
So in the example of voting, what is the trigger that releases the actual count of votes from the endpoint?
You write the chain code. Well, okay, so first off, I would say go back and talk to those guys, but basically the auctioneer still has a role. The auctioneer's role is not to see the data during the auction, but the auctioneer's role is to invoke the time to close the auction function, right? So the different roles, the chain code enforces policies on access to the data, even on the auctioneer when we're building this. And so one of the policies is you only get to close it once, and you don't get to see anything beforehand, and once you close it, you don't accept anything afterwards. And so you end up being able to say, I've closed the auction, now I can do the auditability of all of the votes, or all of the bids that came in. So the auctioneer is given the right to transition the state from open to closed.
And it's largely the same between auction and voting. You've got a commit point, and once that commit is fully committed, then you can do the reveal.
You mentioned that you store the trusted ledger inside P, and in a normal operation of Fabric, if that particular machine goes down, or if there is network disconnection, then you can recover your regular ledger through gossip or some other means, like connecting to other. So how do you recover, in that case, the trusted ledger?
Marcus, Bruno, you want to answer that one? So the question is, if the peer goes down, how do we recover the state of the trusted ledger?
So, I mean, in that ideal case, the trusted ledger contains just freeze up and restore state. That can be done using a mechanism called data sealing, provided by SGX, so that the trusted ledger can seal the data, stores it at the peer.
So there is a repository that contains that data.
So that is, let's say, the subscription way. The other way would be, I mean, we start up same as you would start up a new peer. The peer starts up, the trusted ledger then starts from scratch, and basically you have to get all the blocks into the peer to build up a new view of the blockchain.
And the trusted ledger is rebuilt from the regular ledger?
So,
Yes.
so you can either rebuild it from the regular ledger or you can use the sealed storage.
Okay,
Right.
the storage is out because suppose the machine goes down and it's...
No, the sealed storage writes it to disk.
Non-volatile.
Oh, okay.
So yeah, okay. Let me just. Sealed storage basically is there's a sealing key that's stored inside the enclave, which allows you to encrypt data, and you can take that encrypted data and write it to the disk. Even over reboots, that key is the same, and so as when I restart the machine, I can use that key to unlock the storage.
If the machine is lost, that key is lost.
If the machine is lost, that key is lost, which is
Yeah.
part of the reason, again, the benefits of Fabric is we get the resiliency and the redundancy gives us the availability.
Other question is, of course, you know where this question is going to come from, which is that SGX and T
Side channels.
have been hijacked, breached. So when you have that situation,
So, okay, so let's be clear about something. So the Vipin's question is, what about attacks on hardware-based TEs, right? And this is true of Trust Zone and SGX and all of the others. There are a variety of techniques that can be used to attack it. So number one, make sure that you're applying all of the mitigations for it, right? Okay, that's the obvious thing to do. But the second thing is that, and I'll point out two things. One is that the usages that I'm talking about, the host of the peers is honest but curious, right? So that what we're trying to do is to execute this in a place, in a situation where what we really want is plausible deniability on it. I don't want access to the machine, or I don't want access to the data, and I want to make sure that I can prove to you that I took all of the security protocols that I needed in order to make sure that I can do that, right? So the examples that we're talking about are there. There are no cryptocurrency examples, for example, in this case. The the second answer to that is really that the TEE is never stands on its own any more than anything else that you have for security, right? My HSM may protect my keys, but that doesn't give me a secure encryption environment, right? If I write a bad application, it doesn't matter how good my HSM is, right? I have to combine the two of those together. My HSMs are subject to side channels as well if I need to go after it, right? So what you really have to think of is the entire security context in which this sits, right? So if I'm taking my TEE and I'm running it in, okay, is Hart here? Hart's not here, so I can pick on Stanford. So if I'm taking my TEE and running it in the Stanford Grad Lab, that's a very different situation than if I'm running my TEE on the IBM blockchain in a hosted service where I am paying IBM to limit physical access to the machine. Those are two very different things. And so part of this is you have to understand the security context. When we talk about TEE execution, what we're really talking about is the ability to do optimistic execution for it. So it's really, and again, do we lose integrity if the host is compromised? Well, there's this thing called Fabric, and it has an endorsement policy. So what I get from the TEE is to say, instead of having 13 peers, where I require 9 of the 13, I can take 3, and I require 2 of the 3, right? So I get the efficiencies for it, but I'm still taking advantage of, for the integrity purposes, of what I get from the rest of the application. So yes, it's a very real threat that we have to be concerned about. It is one of many threats that we have to be concerned about.
Okay, I'm told we're out of time, but there will be more. Sorry, we're out of time for this session, but as we said, we have another session right next door. We hope you will all join us there. You can see this in action, and there will be more time for questions after that. Thank you, everyone.